working in a coal mine, going down, 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 working in a coal mine, about to step down, working in a coal mine, going down, 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 working in a coal mine, about to step down.
Okay, so let's do a nice light warm-up here with problem 9.1. We've got a random sample of 100 light bulb lifetimes. The company that produces these light bulbs wants to know if it can claim its light bulbs typically last more than 1,000 burning hours. Let's set up the identify the null and alternative hypotheses for this situation. So I'm going to write these over here. Null hypothesis is that the mean, and because it says it wants to know if they last more than 1,000 hours, we'll just say that the mean is 1,000 hours. We could also say less than, less than or equal to. Actually, let's go ahead and let's do that. Mean is less than or equal to 1,000, and then alternative hypothesis H1 is the mean. We call it the mu naught. This would be mu1 of greater than 1,000. It has to be strictly greater than. The problem says the company wants to know if it can claim that the light bulbs last more than 1,000 hours. Okay, so that part's pretty easy. Setting up our null and alternative. Okay, then to test it, we need to calculate a test statistic. And what we'll do is we'll need a sample mean, sample standard deviation, sample size, degrees of freedom, t-value, and p-value. I'm going to use Excel to do all of this for me. I have to type in a little bit, but Excel will do the math. Okay, so my sample mean is just the average of my sample, which is over here. Sample data. I'll click and drag. I usually like to type, but I want to see where the bottom of this list is, so it goes down to 101. So my sample mean is 991. Ooh, that's not looking good if we're looking for a result greater than 1,000. So we've probably got an idea that we're going to be confirming this null hypothesis, and this company can't make the claim, but let's just run the test to nail it down for certain. Sample standard deviation, then dev.s, and that range is B2 to 101. So there's a sample deviation. Sample size, I could just type in 100, but I like to practice formulas, so I'll just have Excel count that for me. B2 to B101, of course it's 100, and then the degrees of freedom equals the sample size minus 1. We can do that all with Excel formulas. Okay, now let's calculate the t-value, the test statistic. That, remember, all we're doing is having Excel run this calculation. T equals x bar minus mu naught over s, sample standard deviation, divided by square root of n. Okay, so that's what I'm telling Excel to do. Okay, so I'm just going to tell Excel to do this calculation. X bar, that's the sample mean here, minus mu naught, I know that's 1,000. I didn't write it in. I could have put it in the cell above here, but either way, I'll just type in 1,000. Okay, divided by my sample standard deviation, S, over the square root of sample size. Close all those parentheses out. I get a t-value of minus 1 and a p-value of, that's going to be equals t dot dist dot right, because we're only thinking about greater than, so this is a one-tailed test, of that t-value and this number of degrees of freedom. 0.847. Let's show those as percents. That's 85%. That's a huge p-value. So we can't be confident at all. This hypothesis, this null hypothesis is accepted. The alternative hypothesis is rejected. And let me just remind us before we move on what this means in terms of the distribution. So there's our t-distribution. We'll call this t99. We have our test statistic out here at -1 standard error, and we're asking what's the probability that we're going to get something greater than that. Well, it's very likely that we're going to get something greater than that. In fact, it's 85%. 85% of the observations occur to the right of that, including the true population mean. So our sample mean not only is not larger than the population mean, but there's an 85% chance that it lies outside of our area that we would need it to be in to confirm this theory that the light bulbs last more than 1,000 hours. Okay, so high p-value, relatively small test statistic, indicates that we are going to confirm the null hypothesis at all significance levels, okay, at all alphas, because the p-value is not lower than any of the alphas, whether it's 1%, 5%, or 10%. The p-value is huge. Okay, so there's no effect here. We can be pretty confident in that. Okay, problem 9.6. A study is performed in a large southern town to determine whether the average weekly grocery bill per four-person family in the town is significantly different from the national average. A random sample of the weekly grocery bills of two-person families is given in the file. Assume the national average weekly grocery bill for a two-person family is $100. A, identify the null and alternative hypotheses. Let's just pencil those in here. Let's actually put those. Would be that the mean here, our sample mean, is no different to national average, which was given as $100. Would simply be that our mean is different, not equal to 100. Now notice, because we have not equal here, it can be larger or smaller and be significant. So that means we're working with a two-tailed test now. So when we use the t distribution, we're going to use 2t. Okay, and to work the problem, you'll notice what I've done is set up cells for the null hypothesis value. Let's go ahead and type that in, 100. The sample mean, that's just the average of B2 to 101. Okay, and that comes out to 101.52. So far it looks like, hey, that is, the sample mean is different, but remember, we're looking for significance. Is it significantly different than the known national average? So we've got to do our test statistic to find this out. Sample standard deviation, standard dev.sample, B2 to B101. That's in dollars too, so let's put that in dollars. In, it's 100. I could do a count or just type it in. I know it's 100. And my DOF is equal to that minus 1. Okay, so now I can calculate my t value. Equals x bar minus mu naught divided by s over square root of n. Okay, so my t-value is 1.472. I don't know if that's significant or not until I calculate a p-value. So let's calculate a p-value. Equals t dot dist dot 2t. Remember, this is two-tailed. There's my t-value. That's the x. And then the degrees of freedom is that. 14%. Okay, 14%. Chance that I would have gotten those levels of differences just through sampling. And that might seem pretty low, but it's not low enough for our conventional significance levels of 10, 5, or 1%. So in B, it says, is the sample evidence statistically significant? No, it's not. At what significance levels can we reject the null hypothesis? P is greater than 10%, so we can reject it at all the conventional ones, 10, 5, or 1. Okay, if there was a 15% significance level, we could accept it at that, but you'll never see that. You'll typically see 10, 5, and 1. That's pretty much a standard formulation in all of research. Okay, now there's an interesting part C on this question, and it says, for which values of the sample mean, i.e. average weekly grocery bill, would you reject the null hypothesis at the 1% significance level? So in other words, it's saying, what would the sample mean have to be for us to have the p-value equal 1%? For this to equal 1%, how much higher would that sample mean, or lower? Remember, we're just looking for difference. Would that have to be? So, how do we work that out? Well, basically what I want to do is find out what the t-value would be at a 1% for this particular t distribution. So I can solve that. So let me write this down, t-value at 1%. And I can solve that by doing t dot inverse dot 2t probability 0.01, degrees of freedom 99. Okay, so I know my t-value 1% would be 2.626405. Now all I need to do is adjust this number until my t-value equals 2.626. And here's how I would do that. I know it needs to be larger, so let's try a 102. Nope, not quite there yet. 103. Too big. 102.5. A little too small. 102.6. Still too small. I could keep doing that, guessing and checking in 1 cent increments all day. However, if I'm smart, I can tell Excel to do the guess and check for me by using goal seek. So check this out. So here's what I'm going to do. I'm going to go over to Data, What If Analysis, Goal Seek. I'm just going to tell Excel to do a guess and check process, and Excel can do that lightning fast. Well, you'll see it actually, we'll be able to observe it'll take a fraction of a second, but that's a lot faster than I can do it. So what I want to do is set this cell here, the t-value, equal to what I calculated up here. I now have to type it in. You can't use cell reference for this part, but it's 2.6266405 by changing cell sample mean right there, E4, and watch it calculate. Okay, it took less than a second, and it tells me 102.71. So, okay, I can say my max sample bill for 1% would be 102.71. Now that would be if we're looking for just greater than, but because we're looking for differences, we'd have to calculate that for less than as well. So I'm going to do my goal seek again, and this time I'm going to set this t-value to minus 2.6266405 by changing the sample mean. And now it calculates and finds that a min sample value of 97.29 would give me that same t-value and then that same p-value. Okay, and I can double check these by plugging these values back in. So if I plug 102.71, indeed I get a p-value of 1%. So if my bill was just 102.71, if that was my sample mean from over here, I could now say at the 1% significance level that that's significantly different than that national average of 100. Or I can plug in the 97.29. Now, here I'm not getting a p-value, and I think the reason why is because I have a negative number here. So let me see if I can take my absolute value. Yeah, if I take the absolute value of the t-value, I get 1% significance level again. Okay, so they want us to do that for the 1% significance level, and then the 10% significance level. I'll let you do that on your own, but I'll get you started. You would say, what's the t-value at 10%? I want you to do this on your own so you can practice with that goal seek. It's a really powerful tool, and it has a lot more applications than just this, but I want you to get the hang of using it. The t-value at 1% equals t dot inverse dot 2t of now 0.1 for the probability. And again, we're working with a 99 degrees of freedom here in our t distribution 99. So that's 1.66, and then you'll use goal seek to set the t-value to 1.66 by changing the sample mean. Find the max, and then set it to the minus 1.66 by changing this. Find the min. Okay, so now we're looking at problem 9.7. An aircraft manufacturer needs to buy aluminum sheets with an average thickness of 0.05 inch. The manufacturer knows that significantly thinner sheets would be unsafe and considerably thicker sheets would be too heavy. A random sample of 100 sheets from a potential supplier is collected. The thickness of each sheet in the sample is measured in inches and recorded in the file. A. Identify the null and alternative hypotheses for this situation. Well, we're basically seeing whether they're different from 0.05. We can write those down like this. Null hypothesis, the mean is equals 0.05, and the alternative is that it's different. So we can write those down like this. And then we need to just calculate our test statistic. And to make that easy, I'm just going to create categories for everything else on my sample mean, my sample standard deviation, my sample size, and my degrees of freedom. So my sample mean equals average of that, we have 100 again, making life pretty easy on us. My sample size is 100. My DOF is minus 1. My sample standard deviation, standard dev.sample of B2 to B101 is that. Okay, my t-value test statistic is my x bar minus my null hypothesis mean, which I just enter, divided by my standard deviation over square root of my sample size. And from that, my p-value is t dot this dot 2t. Again, we're just looking for a difference, not in one particular direction, so it's a 2t. This t value and this degrees of freedom. And a problem here is that Excel won't calculate a t-dis, it looks like, with a negative number, so I'm just going to change that to the absolute value. And notice what I did there. I nested my t-value function within an absolute value function. Okay, and then the p-value is 0.013 or 1.3%. Let's show that with 2 decimals. Okay, so can we accept that? Can we accept the alternative hypothesis, reject the null hypothesis? Well, not at the 1% level, but yes at the 5% level. And based on that, now we have to make a judgment call. Okay? And the judgment call is which significance level should we use? And in part B it says, based on the results of an appropriate hypothesis test, which we just did, should the aircraft manufacturer buy aluminum sheets from the supplier? What do you think? There's a pretty good chance here. We got like a 98.6% chance that these things vary from the spec. And based on it's an aircraft, we have huge safety concerns there. I'm going to say no. I'll say no. There's a 98.6% chance that the material is not to spec. And given the safety concerns, this is too large of a discrepancy. So, I'm going to say something like that. And then again, it's going to ask us for which values of the sample mean, i.e. average thickness, would the aircraft manufacturer decide to buy sheets from the supplier? Assume a significance level of 5% in answering this question. Okay, and I just, in my judgment, said that we should probably go with a 1% significance level, not 5. But anyhow, we're going to do the same thing we did in the last problem, and that is to use some goal seek to find the whatever sample mean would be at kind of the upper and lower bounds of that 5% alpha level. So I'm going to find first off my t dot inverse dot 2t for 5% probability and then 99 degrees of freedom. That's 1.98, and then I'm going to use again goal seek to set my t value equal to my specified value here, 1.98422, by changing the sample mean, the measured thickness, average. Oops. Okay, so I realized that the goal seek won't work if there's already a value in here, so I have to actually delete my sample mean entry. Okay, I've calculated my my t value for the 5% level. T value at 5% significance. So now I can use the goal seek. I'm going to set the t value down here to the specified level for 5% significance, 1.98422, by changing the sample mean, which I deleted the previous entry because Excel wasn't letting me do this. And there we go. And we've got it. So we've got a sample mean of 0.0479. So that would be the minimum spec at 5% significance, 0.0479. And if we want to think about the maximum spec, we'll do the same thing but set the t value equal to minus 0.198. Let's do that really quick. So I'm going to set that to minus 1.98422 by changing this. And Okay, because I had to really work hard on that one, but I've got 0.05. Whoa, hold on. That's not right at all. Okay, to make that goal-seek work, I have to now take my absolute value off to let this go negative again. So if I do that, I'm going to lose my p-value, but that's okay. So I'm going to do my goal-seek, setting my t-value to minus 1.98422 by changing that. And I get 0.0521. Actually, what I left my absolute value on there, so actually I was doing the negative one first, the left side one first, and then when I took my absolute value off, now I'm doing my right one. And notice my p-value is 5.05. That's probably just a rounding error. Yeah, because I set my t-value to 1.98. Let me try that again. Let's put my t-value to all the decimal points I can. So I'm going to set this to 1.98422 by changing this. And there we go. I've locked in my p-value at exactly 5%. Okay, so there's my range. If I'm interested in making sure that my parts are within spec to 95% to 95% reliability, they've got to be between these two measurements. Okay, so I think we're equipped now to do hypothesis tests for a mean on our own, so I will leave it to you to do problem 9.3.